Hi everyone and welcome to a new video about MOSFET circuits. We continue with our examples and this is our third example. In the example I will look at the P-channel enhancement circuit. We will look at specifically the operating region. We'll look at the operating region like the linear region and the triode region for the specific MOSFET type. Of course, we'll work out everything in our calculation step by step and also verify this in our SPICE simulations. So let's look at our example. We have this circuit here given. We see three resistors, R1, R2 and the RD. You see the type of the P-channel enhancement MOSFET. You see now the arrow is going in, and where the arrow is, you see that this is the source, so you can see the source also. This is the drain and this is the gate. Now you see also the currents are reverse compared to the N-channel MOSFET. You see the gate is going out, drain is going out, and the source is going in. The resistor values are shown here, and the VSS is the DC voltage source here for powering up the circuit. It's all shown here. For the P-channel MOSFET, we see the threshold voltage is given in a negative form, so it is a negative value. And the conduction parameter is given as Kp instead of Kn for the N-channel. In this case, it's 25 milliamps per square volts. We have a couple of things to do. In this case, we would like to calculate the drain current, the source to gate voltage. In this case, is source to gate, not the gate to source, and also source to drain, which is then this, instead of the drain to source for the N channel. In the question B, we would like to know what the range of the RD for constant drain current is. That means linear region or the saturation region in the MOSFET circuits. Okay. Now we start first assuming it is a linear region or a saturation region in the terminology of the MOSFETs. And for that, and for the P-channel MOSFET, we have the following two conditions. One of them is the source to gate voltage must be larger or equal to the absolute value of your threshold voltage. So it must be larger than 1 volt. And this voltage from SD, from the source to drain, must be larger or equal to the source to gate plus the threshold voltage together. That is here given. So we didn't check that, but we will first assume that and we will work it out. So let's look at the solutions. This gate voltage is where we start again. So we start with the gate voltage for question A. So we will use the voltage divider rule for the R1, R2 and the VSS as our voltage source. So we have this, and we can calculate now the 85 kilo ohms over the 100 kilo ohms times the 10, that will give us 8.5 volts. So at the node G, we will see that it will be then 8.5 volts. Now we will now apply the Kirchhoff's voltage law, KVL, at the input loop, this part, or that part of the terms, of course, what you want. Because you can do that in many different ways. Let's then do it from here. That is actually sort of the input and output, to be honest, because you now start at VSS. And then it is VSG and then VG. So it is sort of together. Now we have this voltage expression. Now what we do with this one is we can now use this expression and also the known value for the VG to calculate the VSG, which is one of the unknowns in question A. So we can rewrite this. We say VSG is equal to VSS minus VG. Let's write it down and we get 1.5 volts. So we have now also the source to gate voltage. Okay, that is indeed larger than the absolute value of the threshold voltage, which is then larger than 1 volt. So we can say that we have checked the first condition for assuming the saturation region of operation. The drain current is given by this expression for the P-channel MOSFET. We have a similar equation for a drain current as for the N-channel MOSFET. We see the ID is equal to Kp instead of Kn times the VSG plus V threshold and the quantity squared. So it was in the N-channel VGS minus threshold voltage quantity squared, and then here Kn instead of Kp. So the rest are actually the same. So if we look at the equation, we can say what is the value here. We can use this 0.025 and then 1.5 we have just calculated. It is then plus minus 1, so it just is minus 1 because of the threshold, and you get 6.25 milliamps. So we have also the drain current for the question A. Okay, moving on, and we'll look at the Kirchhoff's voltage law now at the output loop. Why? Because we also want to know the source drain voltage. So we can now set up this equation here for the output. That is the VSS is equal to VSD plus the RD times ID. We know now here actually everything except the VSD. So we can express VSD in terms of the rest of the parameters. You get this expression. So the 10 minus 400 for the RD times the 6.25 milliamps, and you get 7.5 volts. So we have now everything. But check also this, because the second condition requires that. So we will check if this is really larger than the source to gate voltage plus the threshold. 1.5 for the source to gate, minus 1 for the threshold, which is together 0.5 volts. That is indeed larger than, 7.5 volts is indeed larger than 0.5 volts, so this is also valid. So our assumption is correct. So we can say this circuit with these values are indeed operating in, the MOSFET is operating indeed in the saturation region. Okay, now the question B, we'd like to know what the range of the RD is for a constant drain current, because when you make this short, the system or the MOSFET circuit will still work and it is still in the saturation region. But when you increase the value, at some point you will come to the region where we call this the triode region. And that is what we want to know. So for the condition to be able to stay in the saturation region, we say this is really valid, and also this one, but this is important at the moment because that will change. This won't change because the VSG will always be here at this value of 1.5 volts because that is determined by this gate voltage only, and that is also determined by the R1 and R2, which will not change. So we only consider that condition VSD is larger or equal to the VSG plus V threshold, and that is then 0.5. That means the source to drain voltage must be above the 0.5. So if it is at the edge of 0.5, we are also at the edge of from going to the triode region. So from the saturation or the linear region to the triode region. We can also express the VSD using the same formula we have used for this, as VSD is equal to VSS minus ID times RD. Now we can collect these two, and we have then the following expression, which will then produce the condition for the RD, because if this VSD must be larger than this one, VSG plus V threshold, we can put it in here, because this is VSD, must be larger than this. And if I now rewrite this such that I have the RD here, that is the expression now. So that means the RD must be smaller or equal to this expression. So it has a maximum value, maximum allowed value. So if you now substitute the values in here, that will give you, this is of course the 0.5, which is shown here. So that will be 10 minus 0.5 over the 6.25 milliamps, because we want to stay in the constant drain current region. That will give us 1.52 kilo ohms or 1520 ohms. So if I stay below this value, at the edge of the value, my current will be still constant, and I can use this formula. This is really important. This formula is only valid for drain current when you're in the saturation region, which is not valid when you go into the triode region. Okay, let's see more details about this, because we have already done the example. Now we will move on and look at the specific values when you change the drain resistors RD. These are the formulas we can use when we stay in the saturation region. Let's see. For the first case, we know that it's 400 ohms, and then we get 1.5 ohm already for the VSG. And for that condition, we also have the 6.25 milliamps for the ID, and VSD was 7.5 volts. So is it a linear region or saturation region? Yes, that's correct. Now moving on, for example, to a larger value of the RD. Now this 800, double that. The VSG is still 1.5. It is not influenced by the RD. The ID is still also 6.25 milliamps, because that is also the 1.5 minus 1, this formula. And we have now VSD, which is now 5 volts. You can see it is now decreasing, so we need to be careful, and we need to set this VSD value above 0.5, So it is still far away, so it is still in the safe zone. But continuing with our resistor, make it now 1000. You see it is now 3.75. So it is now lower. Still the current is the same because it is above the value of 0.5 for our saturation region. The source gate voltage is still 1.5. That doesn't change. So that is still the same. Now moving on to the next one, which is then 1.2 kilo ohms or 1200 ohms. Again, looking at the VSD directly is 2.5. So that means everything is still the same. So source gate voltage and also the drain current will not change. That still will be still the same as in the first calculated part. But now moving on to the 1.4 kilo ohms or 1400 ohms for the RD, you can see it is still reducing, so it is still decreasing. So what's happening? Let's see. This is now 1.25, still above that 0.5, so the linear region is still valid. Now I need to check the next step. It will be the 1.6 kilo ohms for the RD. Now it is 1.5 still for VSG, but is this correct? ID is now 6.25 milliamps, but there is a VSD of 0. But this must be larger than 0.5, at least 0.5. So if it is 0, I cannot say this is now also linear region of operation, so I cannot use this formula anymore for my current. So this is definitely not correct. So I need to then look at my VSD in a different form. Let's then set up the equation for the VSD. Now this is 10 volts, we know that, and this current here for this drain current is 6.25 milliamps. It will give us 0 volts. Again, this is lower than 0.5 required minimally. So we can see the condition, so it's not valid. So we need to redo the calculations. So for that, I open these two places here. It is still 1.5 for the source to gate, but not for the drain current, 6.25 also not for the source to the drain. So how do we start? We look at the triode region calculations. So we need to use a formula for a different region, which is a triode region, because the saturation region assumption is not valid anymore. For triode region, we have a drain current expression which is given by this. You see that is not anymore a square relationship here for the source to gate voltage, but it is now dependent also on the source to drain voltage. So this dependency is now a little bit more complex than the saturation region. So we need to use this since there is no saturation region of operation. And we see here, and let's call this equation number 1, we see here two unknowns. One of them is the drain current, that is a new value, because it is not 6.25 milliamps anymore. And the VSD is also unknown, because that is also not what we know from other calculations. So we need another equation, and that is the Kirchhoff voltage law for the output. We say VSS is equal to the VSD plus the voltage across RD, or VSD is equal to VSS minus the voltage drop across RD. That's shown here. If I now call this equation number 2, and moving on with the RD of 1.6 kilo ohms for our future calculations, we can substitute this equation number 2 in equation number 1. What happens? We get this. So we see we substitute this VS for this VSD, this expression, you get this here and the quantity here also squared. Now when you work it out a little bit further, and also for your solve for later, we can divide by the Kp now. That will be then this. You have now this expression on the right side. Let's substitute the values we know. We know the Kp. And by the way, we have now only ID as unknown, so we can solve this. We know the Kp because this is 0.025. We know the VSG, that's always 1.5 volts by the way, because it doesn't change. And it is a threshold voltage we know also the VSS, DC voltage source. We know the resistor value for the drain, which is 1.6 kilo ohms. And the rest is also the same here as in this bracket, just squared. Okay, now let's now work it out. It will be then 4D times ID. This is a 1, so 1.5 minus 1 will be 0.5 times 2, 1. So we'll get only this, so you don't need any parentheses anymore. And you will have this expression. You can of course further make it simplify further this one, but you can just directly use the solver here and then solve that. That will give you for the ID drain current exactly 6 milliamps, or a nice number. Now we have the new value for our drain current. Now once we know this, we can use equation number 2 and we say VSD is equal to VSS minus this, RD times ID, and now 1.6 kilo ohms times 0.0066 milliamps will give us 0.40 volts. Or we can now say the new value for our drain current is 6 milliamps, and also the VSD is a new value of 400 millivolts. It is still not a linear region or saturation region, but it is triode region. We have used the correct formula for calculating the VSD and also the ID. Okay, that is the condition for just an example for one of the resistors. If you go up to 1.8 or 2 kilo ohms, you still need to do the same calculations for the similar form, because we are in the triode region now. Alright, now let's collect the values. This is the summary of the values we have. It must be smaller or equal to the 1.52 kilo ohms for the RD and for the other three values we have shown here for question A. Let's look at the simulation results for the question A. We have this. You can see the circuit already drawn here. This is now the P-channel MOSFET symbol. You can see the values, the resistors, and also the VSS. And if I look at the values, what we have, ID is 6.25 milliamps. That's true. ID or IS. You see also the gate current is almost zero, so 1.51 femtoamps, so you can consider that as zero. You see also the gate voltage is 8.5, and also the source to gate voltage from source to gate is 1.5 volts. Also what we have calculated, and also the source to drain is 7.5. So everything is correct here. One important thing about this is the following. This is the model. We use the Shichman-Hodges model or level 1 SPICE model. And this is shown here. That is for, let's say, the very simple hand calculations, very useful. And for that we have the threshold voltage here, which is the -1 volt. So you can just type in yourself here, and then you make actually everything zero to get to the close to ideal condition. There's a beta, so for the SPICE parameter beta here, which is called the Kp in the actual SPICE parameter literature. But the Kp here is different than the K sub p. So Kp, or the beta, is calculated using this. So Kp, K sub p, or is equal to the beta, let's say beta over 2 times the W over L. The W and the L are the width and the length of the MOSFET, of this MOSFET. That is by default 10 micrometers, so we can just use that, but the ratio here is now 1. So we can say Kp is then equal to, or K sub p is equal to Kp over 2. So the SPICE parameter Kp will be then 2 times the value for the conduction parameter given for the MOSFET, which is then 2 times the K sub p. So that means I need to double the value here. So 25 milliamps per square volts must be 50. That's the reason here, you can see that. So we need to use for the beta or the Kp 2 times the K sub p. Okay. That's the result, otherwise you won't get the results, or you need to use more different model for that analysis. Okay. Now going to the question B. And we have now specifically used the largest possible value for the RD, which is 1.52 kilo ohms, which is shown here. You can see the current is exact same. And also the voltage across the source to gate is still 1.5, that doesn't change. But what you see is the source to drain voltage is now exactly 500 millivolts, which is what we wanted, or what we required in the saturation region as the minimum. So this is really the minimum value, and for that you get still the 6.25 milliamps for your ID, and also by the way, the current is correct for the drain current. But if I go up, let's move him up and make it now 1.6, because we did that and we saw it was now 6 milliamps for our drain current. And now we also, the source drain voltage was 400 millivolts. That's all shown here. You see also that the source to gate voltage is not influenced by that, and also the gate voltage, because it's all determined by the R1, R2 and the VSS. Okay. That's also now verified. Let's look at the more details using this graph. You see in this graph we have changed the drain resistance RD from 0 all the way to 2K. And the first plot here is the VSD, and the plot on top is the drain current. You can see the drain current is 6.25 milliamps up to 1000 I must say 1520 ohm for my drain resistance, which is also what we have seen, because this is the condition. Then it will decrease because it will change. It will not be anymore a constant current anymore, constant drain current. You also see the source to drain voltage is exactly here VSS for 0 drain current, is drain resistance, because then we have the VSD is equal to VSS. That's also shown here, but then it will decline or decrease linearly going down and then reach the value of 500 millivolts for the resistor value you have calculated for the drain resistor, which is then 1520 ohms. But then it will change for other values. If I go, for example, to 1.6K, etc., it will not stay or keep decreasing in a linear fashion. So this plot also shows nicely that the region, the saturation region, is up to this point when the current is constant, and the current is now decreasing. You actually enter your triode region. If there are no current at all, let's say there is no current 0 here, 0 there, that is called cutoff. So you have another region in MOSFET operation. Now let's summarize the results we have so far. This is the result for linear region, where we got the original value for RD and also the values. This is the edge of the RD value, is 1.52 kilo ohm, but still linear, so still the formula for the drain current, the square law formula, is still valid. And when you move up, for example, to a little bit higher, 1.6K, then you enter the triode region and you have these values for the VSD and also drain current. And we have calculated that and we have verified that. And these are the results in our table. Alright guys, this is for our P-channel enhancement MOSFET circuit, having the change in the drain resistor situation. And we also calculated the specific drain current, the source to gate, and the source to drain voltage for these conditions. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.